Yes. Thank you, Jennifer. I could very well see my presentation. It's so sweet of you. Okay, this is the very first slide, dear friend. Jennifer, when 30 minutes is over, you can just give me an alarm. I'll stop. Okay?
Sure, Dr.
Yes. Okay, dear friends, let's move forward. As you see the title is all about nanomaterials as catalyst and catalyst for the production of biofuels and biochemicals. Okay, now your question is, what are the nanomaterials that we are going to focus on? Okay, I will be mainly two nanomaterials. One is copper nanoparticles that are used as electrocatalysts for the conversion of CO2 to synthesis gas or methane or ethane, because you know these are industrially important products. Our objective is how to find a substitute for fossil-based fuels. We know fossil-based fuels, we know coal, we know petrol, we know diesel, we know gasoline. Okay, Mr. Trump, as the first citizen, head of the nation, US, always insists that we should resources to renewable resources. This is the content of my talk. As you see, dear friends, I organized my talk in 9 parts. First of all, an introduction to biofuels, followed by how bioethanol can be produced, and then some introduction to conversion of glycerol to 1,3-propanediol, and followed by biodiesel. After that, I'll be focused. After that, on biochemicals. The two biochemicals that I'm going to emphasize are glucose and levulinic acid, because glucose is the economic driver for biorefinery. For the upcoming biorefinery, if we have glucose, that can be used for producing various chemicals. Likewise, levulinic acid. Then same slide. When I say you can move to next slide, you can move, Jenny. Till then, please be on this slide. Okay. After emphasizing something on the use of solid catalysts for the production of glucose, I will be moving forward to the use of polyoxymetallics or hydropoly acids for the conversion of monomeric sugars like glucose, fructose to levulinic acid. And then after talking something about levulinic acid production from glucose and biomass like sugarcane bagasse, cotton, and then sweets, and then miscanthus. After emphasize, we can use polyoxymetallics, also called as hydropolyacids, also called as metalloxen clusters, which were advanced by Japanese scientists like Makoto Misano, Toshio Okuhara, and then by Russian scientists like Ivy Kojauniko. These are the, you know, this solid acid catalyst material called polyoxymetallate, and these polyoxymetallites are underutilized in chemical industry. These are beautiful examples of metalloxen clusters, and typical anion of this polyoxymetallate contains okay, 15 angstroms. 15 angstroms means 1 nanometer. 10 angstroms is 1 nanometer. We have 1.5 nanometer anion. Many chemical conversions, namely Friedel-Crafts alkylation, Friedel-Crafts acylation, okay, alkylation, acylation, hydrolysis, condensation, name any named reaction wherein you need to add acid that can be brought about by these nanoclusters. So I recommend the upcoming youngsters to investigate more on the application of the polyoxymetallites for the conversion of biomass to biofuels and biochemicals. Okay, after talking something on the use of polyoxymetallites for the production of fuels and chemicals, I'll quickly move to the use of solid-based catalysts like strontium oxide and an exotic field like microwave irradiation to produce biodiesel from feedstock like what to say, cooking oil. You see, every day, we generate most of the waste oil in our kitchen. In restaurants too, we generate large amount of waste cooking oil. The waste cooking oil can be effectively converted to biodiesel because by using a simple transesterification reaction using strontium oxide nanoparticles supported on millimetric silica beads, and these millimetric silica beads are coated on deposited with strontium oxide nanoparticles, solid-based catalyst, and a microwave irradiation can bring about the transesterification reaction in seconds. In few seconds, you can convert the waste cooking oil to biodiesel. That is the potential of this. Okay. Many solid-based catalysts have been tested, like calcium oxide, magnesium oxide, many solid acid, and solid base. All have been tested, but under microwave radiation, strontium oxide is the best. And Professor Arun Gedenken's group has richly contributed to this, and he has written a review to Energy and Environmental Science as well, and it has been published with the first author by name Mary Charwin. Mary Charwin and Gedenken has contributed much to biodiesel production under microwave radiation for the accelerated production of biodiesel using strontium oxide as nanoparticles deposited on millimetric silica beads. Likewise, myself and Gedenken have contributed much to the conversion of biomass to bioethanol under exotic fields like sonication, because friends, nowadays is undergoing a transition. Okay, conventionally we do have thermal mode of activation. Now thermal means is not the only means to activate the reaction molecules. We do have various fields like microwave irradiation, so acoustics, ultrasound irradiation, and there are many other fields like plasma, okay, like accelerated electron beam. All these fields can be used for activating reacting molecules as well as activating the catalyst. These are the recent advances in catalysis by the use of different activation fields, different nanomaterials like polyoxymetallate, strontium oxide nanoparticles deposited on silica beads. And finally, after talking something about biodiesel, I will quickly move to the production of activated carbon materials from biomass, and using the activated carbon materials nanoparticles of noble metals. Dear friends, there is no substitute to noble metals as far as electrochemistry is concerned. Platinum is the best when we wanted to do any typical electrochemical reaction. Supercapacitors, okay, but how to find a substitute to noble metals like platinum, okay, ruthenium? We know platinum, ruthenium in Johnson with a catalyst. Okay, that is not the final word. We can find substitute to platinum as well, or at least we can minimize the use of noble metals by developing support materials with high surface area, so that the nanoparticles of noble metals like platinum, ruthenium will be well dispersed on the carbon support and give their best. Okay, within list we can do the best. That is what is called optimization of the amount of noble metals. That is the final part. Okay, yes, Jenny, next slide. Yeah, dear friends, as this production is a closed loop operation, means the net CO2 emissions will be the least, and among various renewable energy sources like hydrothermal, wind, and many other alternate energy sources, biofuels. Earth's surface cellulose is the most abundant carbon source, and it can be competitive to fossil-based fuels, and we can produce almost all fuels that are currently produced in the refinery using fossil-based fuels. Okay, cellulose is such a rich feedstock for producing various biofuels, name gamma-valorolactone or methyl tetrahydrofuran, or okay, gamma-valorolactone, methyl tetrahydrofuran, bioethanol. Cellulosic bioethanol is another opportunity, and Brazil is slowly moving from sugar-based ethanol production to cellulosic ethanol production, and Brazil and US are the two beautiful countries stand out as an example to use biofuels as substitute to fossil-based fuels to make the environment clean and green. Jenny, next slide. Yeah, in this you will see, dear friends, the typical chemical composition of terrestrial biomass. You know, dear friends, with the advance in science and technology, with the growth, with the increasing exponential need for energy sources, okay, the definition of biomass itself is altered. Conventionally, we were thinking that terrestrial lignocellulosic biomass is the only biomass. No, biomass definition itself is being altered, and C1 feedstock like carbon dioxide and like photosynthetic bacteria, like cyanobacteria that can consume carbon dioxide and synthesize carbohydrate, glucose, glycogen. Glucose is stored in cyanobacteria as a glycogen, and that glycogen can be hydrolyzed to glucose, and glucose can be converted to ethanol, and glucose can be converted to levulinic acid. Levulinic acid can be dehydrated to gamma valorolactone, and the cycle goes on and on and on and on and on. And almost all the fuels and chemicals that are currently produced can be produced from biomass, and the biomass definition should be understood in a different way, not the plants that we have unconventional feedstocks like marine macroalgae, freshwater microalgae, bacteria, CO2 that is emanating from industrial emissions, auto exhaust. These challenges, you know, we should take as an opportunity, and what you see, the structure of typical terrestrial biomass. Unlike marine macroalgae and you know, freshwater microalgae, this terrestrial biomass has 30% of lignin, and this lignin is very difficult to be removed. At this point, I should introduce to you a very pioneering chemical engineer by name Professor Tae-Hoon Kim sir, that has been working in Hanyang University, South Korea, and he has done some pioneering work on pretreatment. His work is basically related to biomass pretreatment, and he has developed the aqueous ammonia soaking based techniques and ammonia based techniques for the effective removal of lignin from the biomass. That is the fundamental work that has been done by Professor Tae-Hoon Kim sir, because you know, pretreatment is very, very important for conversion of biomass to biofuels. Jenny, next slide, please. Dear friends, as you know, in the short time of 30 minutes, I have to cover 122 slides, means per second I should at least scan 4 slides. That is the rate at which I should go. There are different platforms at the biorefinery facility that is coming up. We have gas platform. Apart from the thermal platform and sugar platform, another platform should be added at the biorefinery facility, and the third platform is CO2 reduction platform. And I told you, dear friends, even though there are several methods for the conversion of carbon dioxide to fuels and chemicals like photocatalytic, catalytic, the one that stands out is the electrochemical method that is very close to a breakthrough, and like lithium-ion batteries, there is no surprise if we win a Nobel Prize in near future related to the conversion of carbon dioxide to fuels and chemicals using electrochemistry by using copper-based catalysts. Because whenever we talk of electrochemistry, we take back, because you know, all electrochemistry costly catalysts like platinum cells is concerned. In fuel cells, you know, there is no substitute to platinum. But you see, fortunately, in the CO2 reduction, copper nanoparticles and their derivatives are the ideal candidates for synthesis gas. If we have synthesis gas, what not? From synthesis gas, we can produce a variety of chemicals. Synthesis gas has been the starting material at the refinery facility for producing various chemicals, even polymers as well. Okay, at the extreme right on my hand, what you see? What are the feedstocks? What are the materials? And in the middle, you see some kind of chemical molecules. These chemical molecules are nothing but a long chain fatty alkyl ester, FAME, fatty alkyl amyl ester, fatty acid alkyl ester. This is biodiesel. some other molecules such as ethanol, glycerol, and all those things. Jenny, next slide, please. Okay, next slide. Jenny, next slide. Yes. So a comparison of the energy density of bioethanol is shown. Of course, biodiesel has to have higher energy density. The is 31 and 24. Biodiesel not very much difference, not an order of magnitude difference, but few units of difference. Even few units of difference is a difference. So the best fuel is biodiesel, and biodiesel is close to commercialization, and the best feed for producing biodiesel at the industrial level is waste cooking oil, and the best process that you can think of is to use microactivation using strontium oxide nanoparticles that have been deposited very well on millimeter beads of silica, because you know, there will be pressure drop, there will be many other diffusion constraints, thermal gradients, and many chemical engineering problems crop up when you use packed columns, fixed bed packed columns. To overcome that, okay, you should use such bigger particles like millimetric silica beads coated with strontium oxide. Of course, this is the idea developed by Professor Arun Gedenken. Dear friends, I want to emphasize that the name Gedenken in German means idea. As the name implies, Professor Gedenken sir has lived up to his name, and he is full of ideas. When I have landed in Israel, I really do not know anything about biofuels, and what all I have learned, what all I have produced, nearly 35 papers with Professor Arun Gedenken, with a book and 3 edited books and many more. All have been achieved because of the meticulous guidance of Professor Arun Gedenken. He is such a genius, and I would be happy if any other students gets an opportunity to work with Professor Arun Gedenken. Unfortunately, Professor Gedenken has closed his laboratory in Israel owing to his health complications, and he's retired, and of course he is helping any scholars like me by giving guidance, by giving recommendation letters, reference letters that are helpful for earning our livelihood. If I were to go to Korea and win my advanced brain scientific fellowship, and if I were to go to China and work in STT, it is all because of Professor Arun Gedenken sir, that magnanimously and generously provided the these letters are synonymous to the letters that the apostles have given to their disciples on their mission work. Moving forward, dear friends, as I told you, carbon dioxide conversion is one way, and copper stands out, and we can produce this is gas, okay, methane, ethylene, ethanol, all this the reduction of to fuels and chemicals. The industrial feedstock, and different fuels can be. Of course, there are almost there will be always constraints. Okay, the scale at which we can produce, the yields, the selectivity are all issues. I'll show a beautiful example how by controlling and fine tuning the copper size, nanoparticle selectivity from hydrocarbons to synthesis gas, because you know, dear friends, in one instance we would be requiring synthesis gas, in one instance we would be requiring methane. Methane is not synthesis gas is not me, Jenny is not me, I'm not a Jenny. Okay, sui talwar nahi hai, talwar sui nahi hai. It's all okay, depends on what we want. Depending on the product we want, we have to fine tune the nano. Any next slide, please. Just tell me, Jenny, when I have to start 2 minutes before. Take to the acknowledgement slide, and I will finish. Okay. Next slide, please. Next slide, dear friends, is how catalysis can be a potential tool for the conversion of carbon dioxide to synthesis gas, methane, and ethylene. This beautiful, like, prior to this, there is some AFM image. Can you please take me to the AFM image? You have crossed one slide. Please, before this slide. slide, there is one atomic force microscope image. Before this slide, before, okay, I want to say the atomic force microscope. Yes, the atomic force image here. You see A, B, C, D, E, F, and A to F, and you see the particle size is increasing. The particle size is increasing from 1.9 nanometers to 3 nanometers. And this technique to find the size of the copper nanoparticle called inverse micelle emulsion or encapsulation technique. Micelle encapsulation technique is used because the head will be inside and non-polar tail, polystyrene tail will be outside, and the polar heads will encapsulate copper nano, changing the polar head polyvinyl pallidine by increasing the molecular weight of PVP, the dimethyl polymer of PS and PVP. We can fine-tune the structure, the size of copper nanoparticles, and you can see here the size of the copper nanoparticle has been increased from 1.9 to 50. Okay, when the size is 4 or less than 3 nanometers, you get in the electrochemical carbon dioxide synthesis gas. Okay, because there are some issues with this. Low coordination sites will be present once the hydrogen and CO are formed. They cannot come together, and further reduction of CO is not possible when the size is controlled at angstrom level. That is the beauty of nanoscience. By going down, 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 down in the particle size, you can increase the selectivity. If you want synthesis gas, you have to go down. Yes, this linear strip ultramograms. In the linear strip ultramograms, the black line, focus on the black line. This is for the copper nanoparticles with a size 1.5 nanometers. You see the beauty? The yellow color one is the copper foil, bulk. This is the beauty. From bulk, when we go down in nano regime, the current output, the current density is increased. The current density is again a reflection of the amount, the yield of synthesis gas. Synthesis gas. Oh, okay. Next slide, please. Okay. Next slide, please. Yeah, here you see the Faraday efficiency, and the Faraday efficiency is the highest for copper nanoparticles and the football. And the football, what you see is low coordination sites in nanoparticle of size less than 3 nanometers. Next slide. Low coordination sites in copper nanoparticles of less than 3 nanometers. The coordination number is also very important. Unsaturation, degree of unsaturation, unsaturated sites are necessary for the absorption of incoming molecules, and such low coordination sites are facilitating the selective formation of synthesis gas. Yeah, you see the gray colored dots. Next slide, please, quickly. This is the beauty size of copper and producing the product we want. If you have bigger size like 50 meters of copper electrocatalyst, you can produce methane, you can produce ethylene, okay, C2H4. Okay, in the next few slides, I'll show you how ultrasound can be used to accelerate the fermentation process. What is new is, dear friends, there is plenty of room at the bottom. You should remember the lecture by the Nobel laureate that has been awarded the Nobel Prize in 1965 for his contribution to quantum dynamics, Richard Feynman. Richard Feynman, in his remarkable lecture on 29th December 1959, has said that in teaching to American physical, the visionary professor has said that there is plenty of room at the bottom. We all know Richard Feynman, but very few of us know Professor C.S. Lewis. Professor C.S. Lewis has been the professor of linguistics in Magdalen College, Oxford University, UK, and he has written many pioneering works, and one of his masterpieces is Screwtape Letters. Apart from, there is one more landmark publication of Professor C.S. Lewis. Okay, so in Screwtape Letters, Professor C.S. Lewis, because has told me that I should align my talk with my abstract. If you have gone through my abstract, there is a particular mention of an analogy between Professor C.S. Lewis and Professor Richard Feynman, as Richard Feynman has conceived that there is a yes, probably the time is up, so I will my dear friends, what is to present in the next okay, complete in 2 minutes. Just listen to me. Okay, nanoparticles of yeast, Saccharomyces cerevisiae, can also be produced by using unconventional supports like silica and using activating field like ultrasound of particulate, and ethanol productivity can be enhanced in the flow process. Then polyoxymetalates are solid acid catalyst with nano size, and they can be used for conversion of biomass to biochemicals like levulinic acid, glucose, gamma-valerolactone, methyl-tetrahydrofuran, and wherever acid and polyoxymetalates are super acids, and they can be substituted to sulfuric acid for almost all of the organic transformations, name a reaction. Then I told you strontium oxide supported on silica beads is a beautiful catalyst for the conversion of waste cooking oil to biodiesel. Then the last part, I produced activated carbon material of surface area H40 from Lemonia acidisma. Would have shown that when platinum nanoparticles are dispersed on the support, these catalysts are showing long-term stability. The stability has been proved by corona amperometry. Yeah, Jenny, can you please go to the acknowledgement section, because time is up. I will wind up my presentation. Acknowledgement. But not one, please. Yeah, this is nanoist. If in my hand, I would have quickly scanned through. Dear friends, if you have any doubt, inquiry, you can always reach me at Indra Neel P at businessconsultancy.com. Jenny, take me to acknowledgements. Last but not one. Last but one. Yes, dear friends, this is the most important. No, this is the last. Last but one. Yes. Friends, I want to focus your attention. This acknowledgement slide. If I were to have 72 publications to my credit, and a book, and several successful grants, and 4 PhD thesis students, scholars. It is all because of Professor Aharon Gedenken sir, and I'm thankful to Professor Aharon Gedenken sir, Biden University itself, giving me postdoctoral fellowship and providing me the scholarship. I am thankful to my Professor T.K. Vardhan sir and Professor B. Vishwanathan sir for sustaining me for 8 long years by IIT Madras Department of Chemistry. I am happy to thank my postdoctoral supervisor, Professor Tae-Hoon Kim sir at Hanyang University, Korea, for helping me and enabling me to win Advanced Brain Science Scholarship. There I received a salary of nearly 2,30,000 rupees, and I enjoyed the spring. During this time, all around Korea, you'll see beautiful cherries, cherry blossoms. Okay, I'm thankful to Professor Tae-Hoon Kim sir for the wonderful opportunity of Advanced Science Brain Fellowship, Scientific Brain Fellowship. I'm equally thankful to my Chinese teacher and supervisor, Professor Xinling Wang sir, who has been very, very kind to me and has been a great teacher, instrumental in securing me postdoctoral research fund for 2 years in Shanghai Jiaotong University. Dear friends, you should know that Shanghai Jiaotong University is one among the top 5 best universities in China. If I were to get an opportunity to work in such a renowned academic institution, it is because of the efforts of Xinling Wang sir. I am thankful to my friend Chong Chong me to the field of carbon fiber reinforced composites because did not touch upon CFRPs. I am thankful to Dr. Nandanju that has been very, very generous in supporting me in difficult times, right from getting visa to China and right from traveling back from China to India. Like a mother, Dandan was very all to my stay in China, and my stay in China is a joy forever, and it is because of Dr. Dandanju. And then I'm thankful to the staff of library, Central Library IIT Madras, especially Professor Mahendra N. Jadhav sir for giving me all the access to the commercial resources of the library so that I could prepare my talk, I could deliver my talk well. Last but not the least, I'm thankful to Jennifer Lander, as well as Lisa Emily for giving me the wonderful opportunity to share my knowledge on polyoxymetalates, my knowledge on electrochemistry with the learned audience from Saudi and other participants. Last but not the least, I bow down before my Lord and Savior Jesus Christ that has sustained me for the past 45 years amidst many, many uncertainties. Jesus Christ has been the power, the source of knowledge and wisdom thus far. Thank you. Thank you, audience. If any questions, you are most welcome. Jenny, thank you. Now over to the audience.
Thank you, Dr. Neel, for your valuable presentation. If you have any queries, please ask Dr. Indra Neel.
Dear friends, any questions? The participants should have many questions.
Hello.
Yes. Sir.
I am listen. I am audible.
Yes, yes, sir.
I want to know about the what is the catalyst you use to convert the CO2 into the biomass.
Beautiful question. Prakash Yadav sir, I'm very happy that you are here. It's a beautiful question. The work that I discussed in the is basically the pioneering work of Strasser's group that has been published in Journal of American Chemical Society. The reference has all that has been used over there is nanoparticles. But in the slides, you are very correct. I did convert CO2 to useful chemical like formate, sodium formate. In that, to your surprise, Prakash, I did not use reducing agent. I used reducing agent called sodium borohydride, H4, and I proved that sodium borohydride or any borohydride, it could be ammonium borohydride, the coordinating ligand is of least importance. The borohydride anion is the key. What I mean, sodium borohydride very well organic chemists use day in and day out for reducing carbonyl groups and carboxylic acids and all. But they have never tested for CO2 activation. Thermodynamically, it's very, very difficult. It's like hitting Goliath on the head with a stone. The beauty is, I took ammonium carbonate as the precursor for carbon dioxide. Under alkaline conditions, the thermodynamics of CO2 reduction are drastically altered compared to neutral solution. Under alkaline, for example, under alkaline conditions, thermodynamics is feasible. What the delta G, the free energy change, which is positive normally, will be negative in the presence of alkaline environment. Okay, sodium borohydride as such will not generate the alkaline environment. What I did is I put ammonium carbonate in hydrothermal reactor or microwave reactor and added sodium borohydride as the reducing agent. Under alkaline conditions like the presence of ammonia, the thermodynamical parameters are so conducive for the reduction of carbon dioxide to the fuel like formate, sodium formate. Sodium formate, you know very well, it's HCOONA. It's storage media of hydrogen. Okay, so what I mean to say is, when you want to chemically convert carbon dioxide, catalytic means low, low, low. No catalytic means you have to go for asur, forbidden. You have to go for reducing agent. On the contrary, if you want to have electrocatalytic method, you have to go for copper nanoparticles. It also depends on, you know, the field, whether you are using magnetic field, whether you are using radiation field. It all depends on what is the field of activation you are using, and depending on that, you have catalyst. I hope I have answered your question, Prakash. Thank you.
Okay, sir. Thank you.